Yeah, I'm Yaozhu from the National Institute of Informatics, Japan, and this is a joint work with Xuejing and Bruno when I was a PhD student at the University of Hong Kong. And the topic is about type-safe compilation of dynamic inheritance by merging. The first question here is, what is dynamic inheritance? Here we have an example in JavaScript. There is a pattern called mixing pattern in JavaScript that suppose you have a function mixing and it accepts a class as the parameter. Note that this is not an instance but a class itself. And here you return a class extends base, and base here is not a concrete class name but a class variable. We add a new m method that returns 48, for example, here. And this pattern can be very useful if you want to add some features into an existing class. For example, you may have comparable mixing, sortable mixing, and so on. For example, sortable mixing, you may want to mix in a sort function into that base class. A problem here is how to type the dynamic inheritance. Since JavaScript is a dynamically typed language, and hopefully there is a typed version called TypeScript. And the first thing here is that we can declare a type called constructor. This type basically represents an empty class, and literally it means that it has a new, like a constructor accepting any parameters and return an empty object type. And we can type the mixing function with a generic one that we declare a type parameter t-base that extends that empty class type. And you can regard t-base as the interface, and base is a class that satisfies that interface t-base. Here, one thing we want to note is that if m exists in base, then that one in base will be overridden by the new one in the mixing. And it should be very natural because almost every existing language follows this pattern of overloading. But this overloading is unsafe. Here is an example showing that why the overriding is unsafe. And we have a new class A. A already have two methods, m and n. The m method returns a string, like here, full bar. And the n method will return the uppercase of that string. So you may notice that there is a dependency like the arrow implies. And then we use the mixing function with A as the base class as a type parameter, as the parameter, sorry. And since here, the new m in mixing function will override the one in class A, then the dependency becomes the method n in A, and it depends on the new method in mixing. It will cause a runtime error because here m is expected to return a string, but the overridden one returns a number instead. That's why this code is type unsafe. Yeah. And a takeaway from this example is that implicit overriding is very dangerous. This example is for type safety, but if we recall the fragile base class problem, it can also cause some problem in the semantics. We will also explain this in the next example. And here we advocate a trait model with merging, which has two features. One is it will keep both behavior if there is no conflict, and it will require explicit resolution if there are conflicts, like what we have in last example. To be concrete, we will rewrite the example in our language called CP. Here, mixing has a different representation. I mean, we type it differently. Here, you can ignore the star mint part here because it does not mean too much thing here in this example. And the thing interesting is that we also have base as has a variable. Here is not a class but a trait because we have mentioned before that we have a trait model. And the class A is represented as this MKA. The M method is still a string full bar, and N is still a it still calls a function to uppercase with this dot M as the argument. But the result is different because the two M fields coexist because we suppose they have disjoint types. That means string and int does not overlap with each other. We can safely have them both in the new in the result O. This is the example for non-conflicting cases. But if you have conflicting cases, for example, here you have a mixing that adds a new method M with type string instead of the integer before. Then you can see the new M actually conflicts with the old M. And we want to avoid this implicit overriding semantics. So actually, we want to express the absence by disjointness that we suppose the base class do not have such conflicting method M with type string. And our type checker will detect such conflict and emit a warning that the two M methods actually have non-disjointness type, and they are rejected by our type checker. This is a way we keep our language CP type safe. And you may ask further, why merging matters so much in our language? And actually, it enables another feature called family polymorphism, and that can solve the expression problem very easily in CP. Basically, we will not dive into the expression problem here because time is limited. But the impression is that you have two dimensions. The x-axis here is for operation. You want to extend the operation modularly. And you also want to extend the expression modularly, like you have the numeric literals and the addition. And for operations, we currently have evaluation and printing, pretty printing. In CP, it's very elegant because if we have the 4 traits before, then we can directly merge them to have a merged trait having all the 4 features in 2 dimensions. And our work focused on the compilation for merges. It's type safe, but how to make it more efficient is also a good question. The previous work will use a nested pair, like a binary tree. And the problem is, if you want to get the eval add part, the lookup is very slow because you need to go deep into the tree to find the leaf nodes. But our representation wants to solve this using a extensible record. Here, our solution is inspired by the name mangling, for example, in C++. For example, if you have many overloaded functions, you will mangle the name into different strings to distinguish them. And here, we call such mangled string type indices with the blue font here. And here, every type is mangled into a string as a record label. This is possible because our type checker ensures the expression to be merged has disjoint types. And then their type indices must not conflict here. Another advantage of our approach is about order sensitivity. Here, if we swap the merges like this, actually we need to adjust the binary tree, or you call nested pairs, to reflect the differences. So basically, we have different pairs for the two essentially same merges, but with the different order. But the compiled records are actually equivalent, and we can benefit from this actually with optimization we will explain very soon. The key ideas is to compile the merges to extensible records with type indices as labels. And in this way, we can compile dynamic merge operator to runtime record concatenation. And since our language involves a lot of type coercion, or called type conversion, as you want, typecasts, or any other words. And this feature is compiled into record filtering or reconstruction because our subtyping is more complicated with distributivity over the intersection types. And the second benefit we mentioned before can enable optimization that coercions between equivalent types can be avoided. For example, top-like types are all equivalent. Top-like types are actually the supertype of top, both supertype and subtype of top. And the intersection types are all equivalent up to permutation, duplication, and top-like type removal. This is because the records are unordered and the labels are unique. We also did benchmarking, and we find all optimizations in our work in practice. Well, the most important one is the one we mentioned, the coercion elimination for equivalent types. And CP is slightly slower than handwritten JavaScript. That's not surprising, but we are not so slow. That the most slow up here is 3 times. And most one are around 1.1 or 2 times lower. The exciting thing here is CP has the most smooth curve with regard to the inheritance level in the region example. And it means that our inheritance model is very efficient. And we have more in the paper. For example, complete examples for the type safety issue in TypeScript, compilation scheme for parametric polymorphism. And we have formalized the compilation scheme with the rock prover. We have implemented prototype CP compiler targeting JavaScript. And you can find detailed discussion on the implementation and find more optimizations here. You can scan the QR code to find our benchmarking suite, prototype implementation, and the formalization in Rock. Thank you very much for your attention. Please feel free to ask me any questions.
Thank you. Maybe we'll have time for one question. Somebody, yeah.
Thanks for the talk. So when you compared to JavaScript, what is it exactly that you compared? Was it dynamic inheritance in JavaScript or something else?
Yeah, for maybe I haven't mentioned, the dynamic inheritance is compiled to merges. And actually, if you write class in extend something, actually we have like class A merged with class B. A is the current class you have in the body, and B is the inherited class.
So your benchmarks, they show that this approach is faster than doing it the JavaScript way, right?
Oh.
Or is that? Mm-hmm.
Right, yeah, our benchmarking implies that result. But we want to mention that the handwritten JavaScript one is also in the similar style with us. If maybe you can look into the example to have more deep understanding on that. But actually, it may be not so idiomatic in JavaScript.
Okay.
Yeah.
Sure.
Yeah.
Thanks.
Yeah. Yeah. By the way, it's also for the sake that it must satisfy the expression problem.
Okay, maybe carry the discussion
sure.
offline. Okay, thank you.
Yeah. Thank you very much.